So I guess we can probably get started. That was like the longest 10 minutes ever, actually. My name is Brian Duff. I work for Google on the Android context team. And I lead a couple of APIs in Google called Awareness and Nearby. And I wanted to talk to you a little bit today about some of the ways, like what these APIs are, and some of the ways that you can use these APIs to make your applications more contextual. So here's some of what I'm going to talk about. I wanted to start off by sort of giving a little bit of history and background behind the projects, in particular the Nearby project. Then we'll look at a couple of the components of Nearby. So Nearby Messages, which is a simple API for passing small amounts of information between devices that are near each other. And Nearby Notifications, which lets you attach app and site information to Bluetooth Low Energy beacons. And then I'm going to talk about the Awareness API, which is a really general purpose API for listening for semantic context and triggering app experiences based on that. And then I'm going to talk a little bit about some of the stuff that we have coming soon in the future. So we started the Nearby project with a really simple idea. The interactions that we have in the real world are really straightforward. Like you walk up to people and you talk to them. At a conference like this, you can introduce yourself to somebody really easily just by walking up to them and talking. But when we try to do the same interactions with our devices, it can be kind of clunky and unpleasant. There's a lot of friction. Like if we actually started on the Nearby team as part of the Google Plus team in the social effort, and like our original goal was to try to make it really easy for people to connect with each other. So we're looking at ways for you to sort of just add people to your circles really easily when you were standing next to them. And so these fundamental activities that we take for granted in the real world on our devices often involve things like trying to line up the NFC sensors on our phones or typing email addresses into our phone on the little keyboard that we have there, our phone numbers and so on. And we wanted to make this a much more magical kind of experience. So when you think about this kind of proximity technology, the really obvious technology to use there is Bluetooth. Bluetooth is a radio technology. It works at around 2.4 gigahertz and travels around 100 feet, which is a pretty far distance. One of the things that we noticed when we started the Nearby project was that a lot of Android devices actually at that time supported only Bluetooth Classic, which is a technology you sort of know from whenever you pair your headphones to your phone or you pair your phone to your car. And it allows you to do simple things like advertise the presence of a device and scan for nearby devices. So there's a kind of hacky thing that you can do there where you encode a bunch of information in the name of the device and you make the device discoverable, and another device is scanned and you can get information that way. More modern devices actually have support for Bluetooth Low Energy, which is a more formal way of doing this, where there's an advertising format and devices can advertise data and scan in a fairly low power way. But one of the things that, think about that interaction I mentioned before where you just sort of walk up to things and use them. One of the things we'd really like to do is to sort of limit the range, and the 100 feet thing is kind of a problem. Like, is it possible for us to say with certainty that two devices are actually in the same room as each other using Bluetooth? It turns out it's kind of possible. There's a way you can approximate this using the signal strength. So you can look at as you receive a Bluetooth signal on a device, you can look at the strength that you received that signal at, and you can take into account the power it was transmitted at, and you can approximate how far apart those devices are. But it turns out radio signals do really interesting things. They bounce off walls, and if they bounce off a wall, you can sort of imagine it takes twice as long for the radio signal to reach its destination, and its power is kind of halved if it bounced one time. And similarly, we're all kind of like walking bags of water, and as radio signals go through us, they get slowed down and they change, and so the signal strength that we measure on the other end is different from a direct path. This is a problem that we call multipath, and it makes it really hard to accurately determine the distance between things using radio technologies alone. So we'd really like to say like these two devices are in the same room as each other. So one of the ways that we figured out we could use to do that is simply using audio. And it's a really obvious technology to use for this. If you think about, if I'm standing in the same room as you and I talk to you, you can hear me if you're in that room, but if you're outside, unless I'm yelling at the top of my voice or I'm using a microphone, you probably can't hear me from outside. So we built a bunch of prototypes using audio. We sort of came up with a scheme to, just like the old-fashioned modems where you sort of turn data into sound, and we had Android devices that transmitted this sound, and we could decode that on the other end. This was something that we managed to really irritate all the other teams sitting around us with. Google's really into having us work in these kinds of open office spaces, and so our early prototypes of this emitted this really unpleasant, grating, screechy noise that was sort of annoying to other teams. So we proved that we could make it work, but we needed to do something else to make this something that we could actually launch outside of Google. So we worked really closely with a team in Google Research to sort of make our audio modem move the frequency of the audio up to around about the 20 kilohertz range. And this is high enough that most people can't hear it. It also, because it's such a high frequency sound, it actually is even worse at going through walls than regular audio, which makes it even better suited for that use case of being in the same room. So this is a video that I'm not going to attempt to play, but you can see here, this is, because you can't hear this signal, this is a spectrum analysis of what it looks like. You can see there's a sort of peak of data around the 90 to 20 kilohertz range. As I say, like most people can't hear sound at this range. We actually had a couple of like ridiculously young interns on the team when we started the project, and the way they described it is that they could actually kind of feel the sound rather than hear it. They were really useful when we were debugging this in the early days, because we could ask them like, can you hear it? Is it actually working? Is this thing on? You know, that kind of stuff. So it's actually far from obvious though. Like once we got this working with sort of near ultrasound on the devices that we had, which at that time were like, to tell you sort of how long ago this was like Nexus 4 devices. We got it working on our Nexus 4s, but it was far from obvious that this would actually work on all the Android devices out there. And you know, sort of why should it? Because like the audio on your device is not really typically designed to handle audio at this range. So to sort of prove this out, what we did is we just bought a ridiculous number of Android phones of every conceivable type, and myself and others on the team, we just ran around the Google campus with big handfuls of devices and tested this out in every sort of environment that we could possibly try it in. And it actually turns out with a little bit of refinement and tweaking, we were able to make this work pretty reliably across most Android devices. So the problem, however, with both of these technologies, the Bluetooth beaconing mechanism and the audio mechanism, is that we can only transmit really small amounts of data between devices this way. The audio one is limited by reliability. If you send more data, the reliability decreases almost linearly with the length of the data, and so we have to limit it to a fairly small amount of data in order to make sure that the signal gets across. And similarly, Bluetooth is sort of limited by its specification in terms of how much data you can send. So the really obvious thing to do there is instead of sending the data directly between the devices, you just send the data up to the cloud and you send some kind of a token between the devices. So we built this thing that's, it's actually kind of a surprisingly complex backend system that at its core is really just a distributed hash map in the cloud. And the way this works is when one device wants to transmit information to other devices nearby, it either generates or retrieves a token from the server, it transmits that token over either Bluetooth or audio, and sends the data up to the cloud associated with that token. Other devices nearby then listen on the microphone or scan over Bluetooth, and when they hear a token, they decode it and can just request it from the server. And the assumption is that if you're close enough to get this token, you're authorized to get the data. Of course, we optimistically assumed that Nearby was going to be immensely successful, so we designed the length of these tokens to make it sort of extremely unlikely that they would collide with each other, and extremely hard to guess. The data is only stored on the server for a limited period of time. So we were having a lot of fun at this point, and by this point we had actually moved from Google Plus to the Android team, and we'd been sort of just like enjoying like building this technology just for technology's sake. But we started thinking again about like what are the use cases for this. And as I said before, we'd started with this like identity sharing model where you could sort of broadcast your identity to people around you and they could connect with you. It turned out when we tried that inside Google, people found it kind of creepy. It's maybe not that surprising to everybody, but yeah. So we started thinking about devices, because really, if you think about all the devices in your life, there's a lot of interactions that you have with those devices which are kind of, they're possible, but they have a lot of friction. So one example, Google has most of you probably know about Chromecast. Chromecast is a device that you kind of plug into your television and you can cast content from your mobile device to it. This works really well if you're on the same Wi-Fi network as the Chromecast device. That's sort of a prerequisite to casting. However, there are use cases where, like, if you're a guest at somebody's house or you're in a public space where there's a Chromecast device, the awkwardness of trying to sort of get onto the person's Wi-Fi network and typing in hexadecimal Wi-Fi codes or whatever is kind of painful. So again, it's possible, but it has friction, and we'd like to make this as frictionless as possible. So ideally, you can just walk up to a Chromecast and you can cast to it. So we built this feature called Chromecast Guest Mode on top of the Nearby technology. And the way this works is the Chromecast device and the phone are doing Wi-Fi scans periodically, and they do those in order to sort of determine that the phone is near the Wi-Fi device and the Chromecast device. And if they get some kind of a correlation, then we start emitting the near ultrasound signal from the television, and we light up the cast button on the phone. And when you click on the cast button on the phone, then we turn on the microphone. And if we're able to hear the ultrasound signal, then we allow you to cast directly to the Chromecast device. And there's also a fallback using a 4-digit PIN code, which is a little bit a little bit more low tech, but it works pretty well as a fallback. And this is for cases where like the television may have the volume turned all the way down, or there's some set of televisions that maybe don't support the frequency range. So since it worked pretty well for that use case, we actually built a couple of other things as well, but we figured the best thing we could do at that point was to take all of the sort of grungy signal processing work that we did and the sort of dealing with the radio stack and the Bluetooth stack on Android, and just encapsulate it in a simple API, and then publish that API to developers, and sort of then pass the buck and say, like, you go ahead, developers, and like build really cool things with this. And I've got to say, like, in my career, it's like one of the most rewarding things that I've been able to do is build APIs like this, because I can only imagine a sort of finite number of things that I can build with a given technology. But it's really amazing when you build an API and Android developers or iOS developers all over the world kind of build really cool things with it that you didn't really expect. So a couple of years ago, we released the Nearby Messages API, which is the thing that encapsulates all of the stuff I've been talking about. We released it on both Android and iOS simultaneously. Having it work on iOS is really important to us because we want to make this work for all devices. And so we're excited to see a whole bunch of apps using this API. Some applications are using it for sort of finding things around you. Other applications are using it for that sort of main use case that I mentioned before of like sharing things between nearby users. And then a really popular segment that sort of surprised us a little bit was sort of games. Like a lot of games have find players nearby features that use nearby. So I wanted to dive a little bit more deeply into what those APIs look like. So let's go write some code and see how easy it is to add this to applications. So look, it's really simple. It's just like one line of code. You should totally do this. It's like the easiest thing ever. Of course, I'm being a little bit dishonest with this because there's like 20 or 30 lines of boilerplate code that you have to do before this to create the end client thing. So this is a Google Play Services API. So you have to create like a Google API client first, but it's a pretty standard set of like preamble. And this is how a device publishes a message to other devices nearby. You basically simply pass the bytes into this message object and then say publish. The content can be up to 100 kilobytes. It's a fairly arbitrary upper limit. The main reason for that limit is just that we didn't want to turn this into like a transient cloud storage system that people could use for just storing arbitrary data. There's also a bunch of options that you can pass into this API. So by default, this will do the best it can to get this information to nearby devices. It will use Bluetooth, it will use both Bluetooth Classic and LE and audio. But you can also pass flags into this to say, I only want this to work in earshot range, which will limit it to ultrasound. And there's also some other more complex options you can pass in. So on the other side, this is what it looks like. You define this message listener callback. When we see a message that matches whatever the criteria you set up are, we call this onFound method. We pass you the message, and you can get the content from the message really simply. And that's how you subscribe. And again, there's a bunch of things you can pass in here, but this is the sort of main path. So another technology that's become really popular in the last couple of years are BLE beacons, so Bluetooth Low Energy beacons. And these are small battery-operated devices that they last on battery for like maybe a couple of years or so, and they just constantly advertise using BLE. And you can sort of attach them to objects in the real world. The way that you sort of set up these beacons, if you have a small enough amount of data, you can just encode it on the beacon itself. Like shortened URLs, for example, will often fit into the advertising packet. But more commonly, the beacons are transmitting some kind of a UUID, and then there's an association between that UUID and some larger piece of content in the cloud. And Google actually have a whole bunch of infrastructure around beacons. There's a beacon platform which allows you to attach things to beacons, and Google has a standard beacon format called Eddystone. So the general idea is that you can sort of mark up the world with contextual content using beacons. So there's a bunch of ways on Android that you can scan for beacons and sort of understand what's around you in terms of the sort of beacon space. The most obvious one is what we kind of call the low-level API, which is the Bluetooth Scanner API in Android. I'm never sure if I pronounced that properly. It's probably Bluetooth LE Scanner. It sounds kind of French, Bluetooth Scanner. Anyway, the Bluetooth Low Energy Scanner API it gives you a fairly, it sort of allows your application in to do a Bluetooth scan and to get results back. But we built a bunch of stuff into Nearby Messages to make this easier for applications and also to provide some features that the low-level API doesn't provide. And if you think about it, this type of use case actually maps pretty well onto the model of Nearby Messages. You can sort of think of these beacons as publishers that are just publishing the same content all the time, and so the subscribe part of the API maps really well onto your application and getting the content. So one of the things that we do as part of the Nearby Messages API, for example, is when we see an Eddystone beacon, we can resolve the Eddystone ID in Google's backend servers and give your application the content directly, so you don't have to look it up on the cloud yourself. There's a bunch of other advantages of using this API over the low-level API. One of them is the permission story is a little easier. Android, I think, collectively made a kind of an odd choice, I guess, around permissions prior to Lollipop, where you had to have the Bluetooth admin permission in order to do Bluetooth Low Energy scans. This was corrected in later versions of Android, but we wanted to sort of take away that restriction even for older versions of Android. So because Google Play Services can sort of like take care of permissions for you, you can use the Nearby Messages API to do scanning even on versions prior to Lollipop without having that permission. Another sort of advantage to using this is that you get free stuff. We like to give you free stuff. So free scans. There are lots of other applications potentially that are scanning for Bluetooth LE. The system itself actually scans periodically for location services. And if we happen to see something while we're scanning that matches whatever your app is interested in, we'll deliver that to your app. And this is in contrast to the low-level API, where you only get scans when you're directly scanning, basically. The other thing is that you might have noticed that sort of, especially starting in Android O, there's a lot of focus on battery and sort of restricting what applications can do in the background more and more. So increasingly, like the model is, instead of your application running a background service and doing lots of work in the background, you're expected to sort of register with things in Android that will wake you up when it makes sense for your application to do processing. So Nearby Messages is actually one of those kinds of APIs where you can say, one of the things that I'm interested in are beacons, and we'll wait. Your application can register a subscriber for beacons in the background, and we'll wake your application back up again once we see a beacon that matches your requirements. So this is an example of how you go about subscribing for beacons. So the main sort of key thing here is that the options that we're passing in here, we say BLE only, and this is our hint to the API that we don't want to use high power technologies like audio and Bluetooth Classic. We're only interested in Bluetooth Low Energy. This puts our API into sort of a low power background mode, and then when you call the subscribe API, in addition to these options, you also instead of passing in the message listener callback, you pass a pending intent. So pending intents are a mechanism for your application to say to us, I'm giving you permission to send this intent to me at some point in the future. This sort of like is a little bit similar to the way the system might send a broadcast intent, except that this is really targeted. If we did this via broadcast intents, any application on the system could sort of lie to you and tell you that there's a beacon. With this, you're basically giving us a targeted permission to send you an intent when we see a beacon that matches your requirements. And so this is how you handle the intent when it comes in. Intents are a really kind of yucky API to use in general. So there's a bunch of stuff that's encoded on the extras of this intent that sort of tell you about what we found. Rather than making you pick through the extras and deal with that yourself, we instead provide this kind of wrapper API that you pass the intent into it and it unpacks it and then calls the message listener back that you specify with these onFound and onLost callbacks and passes the message in. One of the things I should mention this here is specifically for beacons, you're also able to tell when the beacon goes away, so you can listen for presence essentially. You can fence things on this. So far the examples that I've given, they're only going to find beacons that are that have attachments which are associated with the same dev console project as your application, and it turns out that there's actually there's a way to create public attachments, and public attachments are sort of they're namespaced attachments that any application is able to subscribe for. And so there's an optional part of the subscribe API where you can pass a message filter, and in the message filter you can say things like, I'm interested in attachments in this particular namespace. There's also a way for you to sort of scan for the raw beacon identifiers. So this is if you don't want to use Google's beacon infrastructure to store the payload, you can store it in your own cloud and use this low-level API. And it's not as low-level as it still gives you all the benefits that I talked about earlier over the Bluetooth with Scanner API, but gives you the sort of the raw data that we get back from the beacon. There's also a couple of special callbacks that we provide for the beacon case. We can actually we can listen for the signal strength changing over time. I mentioned earlier that it's really hard to approximate distance, but we do the best that we can essentially with that. And the way that we've sort of gone about doing that is to sort of calibrate a huge number of devices and build a sort of calibration model of correlation between RSSI and distance, and we try to give you a sort of approximation of how far apart, how far away you are from the beacon, and we call you back as that changes over time. So I want to just give this example of this is the scanning for the low-level beacon IDs case. In this case, you can scan for Eddystone IDs. You can also scan for iBeacon IDs. So this is how you would scan for iBeacons. So when you receive the message in this case in the onFind method, instead of getting the bytes from the message here, the message in this case actually represents the beacon itself, and we can convert it into an iBeacon ID. And from that iBeacon ID, we can get a bunch of information about the actual physical beacon. So one sort of limitation that sort of both of these APIs have, and many APIs have in general, is that your application needs to be installed on the user's device in order to use them. And if you think about that, it doesn't really meet the requirement that we talked about at the start around just walking up to things and using them. Maybe the best experience for users includes an app that they don't have. And so imagine I'm in the local coffee shop. This is a totally made up example. But imagine I'm in the local coffee shop and I'm waiting in line. And if only I had the application from that coffee shop on my phone, I could just order my coffee and then go sit down and wait for it to be ready. How do I know that there's an application, and how do I know that it provides that functionality if I don't already have the app installed? So we created a program last year that we talked about at Google I/O called Nearby Notifications that provides exactly this functionality for applications. So the idea behind this is that you can attach websites or applications to Bluetooth Low Energy beacons. And if we consider the application or the site to be very relevant to users, the Android system will show notification to users that allows them to either go to the website or install the app. So you can think of this as sort of like a proximity trigger deep linking functionality. One of the sort of use cases that we found this really helpful for was setting up new devices. So we actually built a bunch of baked-in usages of nearby notifications around the devices that Google provides. So here's an example of like before you can set up your Google Cast device, you need to install the Google Home app. So when we see a Google Cast device that's in setup mode, we just show this notification in Android. You can click on this and it will take you into the Home app or install it if you don't have it installed and take you to the right place to set up your new device. So the Nearby Notifications API and platform really allow your app to have this kind of experience. You set this up, it's really easy to set up. So you use the Beacon dashboard. There's a chunk of JSON that you set up that tells us about the appearance of your notification, the behavior that you want it to trigger, and you can also set up some targeting rules. So you can say, I only want this to appear under these circumstances. One sort of caveat is that for URLs, there's some restrictions around the kinds of URLs you can set, you can advertise. So they have to be HTTPS URLs, and they have to be crawlable as well. So we get metadata from the website, and so in order to show that information in the notification, you have to, if you have a no robots .txt set up, we can't crawl the site, so you have to have that set up. One thing that I always like to point out is that it's a really this is a really powerful way for you to get your application installed in a really relevant context, but it's a really big responsibility. Google Play Services is approaching like 2 billion devices at this point, and that's a really large user footprint. We have to be really good stewards of the user's attention, and notifications are one of those areas where people often get irritated if things are spammy and annoying in the notification tree. So we have a bunch of guidelines around how to write notifications that are really relevant, and we have a model that sort of scores notifications based on how relevant we think they are. The most obvious thing is really just the more contextual you can make your notification and the more targeted it is, the better, the more chance of it will be promoted to the level of a notification. So the coffee example that I gave before is probably a really good example. We have seen examples where there are these really powerful beacons that are emitting something that in the mall like advertises a store and tries to get people to come into the store, and these generally perform far worse than this kind of use case. The other thing is, like, if you try to make the user experience as smooth as possible when people do click on the notification. We saw some examples in the past of notifications where you click on them and you install an app, and then it drops you into the login screen in the app, and then you have to register for an account, and then you have to like verify your email address, and then you have to go in. This kind of like extended flow as a contextual experience is really jarring, and so like the more like direct, I guess the more of a direct place you can take users to in your app, the better. So these are some of the things that make notifications perform better. So this is what the attachment looks like for this. So here we have a simple, this is, by the way, the title of this notification is not probably not a good example of a title, but you'd probably say something more relevant to the use case that you're trying to sort of enable. But this is an example. This notification has a title that will show the URL here could either be an HTTPS URL, or in this case it's an intent into a particular place in your app. And then there's a bunch of optional targeting rules here. So this one is saying only show this notification for users who don't already have this application installed, and only show it between 9 a.m. and 5 p.m. And there's a bunch of other things you can specify here, and the developer, the Google Dev site link I'm going to show later has more examples of that. So we've talked a lot about proximity between nearby devices, and that's kind of one type of context that your application might be interested in. There are lots of, your device has a lot of sensors, and it actually understands a fair amount of the world around it, but the APIs that we provide in general will expose this data to you at a fairly low level. So an example is accelerometer data, where you can get information about the movement of your device through space. That data is kind of low level, and it would be kind of useful if you could combine that with higher level information. So for example, if you know that the user is walking and they're in a particular location, there may be certain kinds of use cases that you could enable in your app. So the Awareness API is a way for your app to basically set up conditions in the real world that you're interested in that will wake your app up for, and also to allow your app to sort of query about the world around it. So this diagram, I kind of stole this slide from last year's Google I/O presentation, but this is showing sort of the symbols for like around about 9 of the APIs that we provide just in terms of location and context related APIs in Android. And one of the things that we do is we tie all these APIs together. So we make it possible for you to basically combine them together in a way that's really efficient. And the efficiency that we're talking about here is kind of a battery efficiency primarily. So I'll give a really contrived example, but say you want to be able to tell when somebody's in a particular location at a particular time of day. If you're not being careful, you could just set up a location fence that runs all the time, and then inside, when you receive the callback, then you check the time of day. And of course, you would never do this, of course, because it's kind of simple. It's a simple example. But as you combine more and more different kinds of fences together, it becomes less and less obvious how to optimize the set of sensors that you're listening to in a way that's going to save as much battery power as possible. So the awareness API, you can think of it as like a query optimizer, basically, where you tell us about the things that you're interested in, and then we optimize the way that we scan and we look at all the sensors, and we aggregate that across different applications so we can kind of share things where there's overlaps, and then we call you back without draining the user's battery too much. So again, with the contrived examples, I have another really simple contrived example of but this is just an illustration of like one way to use the API. So imagine that I wanted to like automatically play a particular playlist that I have when I'm at my local coffee shop on a Saturday afternoon when I have my headphones plugged in. I missed out the headphones from the slide. But, so here's how we do that with awareness. So the API is really centered around this concept of fences. So we set up simple fences for the sort of primitive things that we care about. So first of all, we care about when the user is still, and there's a sort of there's a default amount of time that we consider them to be still. The time threshold that we consider them to be still. Then you can set up a location fence. So the location fence is saying, this is the lat longs, the center of the lat long area that I care about. I care about a 50 meter radius around that location, and the user has to have been in that location for at least 5 minutes. And then the third fence here is a really simple one, which is just saying the user must have their headphones plugged in. So then you combine, so the awareness API basically provides logical operators for combining these low-level fences together. So in this case, we're anding the three conditions together. We're saying like all three of these things must be true before you wake up the app. So once we've created our kind of combined fence, we call the update fences API to register that with the system. And you'll notice again, we're passing in a pending intent here, and this is again, to allow the system to wake us up when this fence triggers. So we've had a lot of feedback about nearby and awareness in general from developers, and one of the reasons that I'm here today is that we want to get more feedback, and we want to know how we can make these APIs even more useful to applications. We want to know the kind of things that you're building with the APIs, and we want to know when they're not working and when they're insufficient for things too. Based on some of the feedback that we've got, particularly for nearby, there's a bunch of feedback we got around, for example, the fact that it requires a connection. And so, some of these things we've been taking really seriously, and we've been working really hard on trying to address them. We have some really exciting things that we're going to talk about next month at Google I/O. So if you're able to attend, or you're able to tune into the live stream, we have a session called Enabling Contextual App Experiences, where we're really excited to introduce some new stuff in nearby. We also, really would like you to reach out to us. So I have some sort of like, let me just jump to it. We have some contact information here. So if you have technical questions about nearby awareness, the Stack Overflow is actually a really good place. We all kind of hang out in there, and we like sort of answering technical questions there. You can also reach out to us at androidcontext@google.com. This is not a support thing. We probably won't respond to those kinds of things, but if you have suggestions, or you want to share use cases with us, or you want to tell us about things you'd really like us to build, please reach out to us at this address. You can follow me on Twitter if you like. And these two sites have lots of examples and sample apps and other information about how to use the APIs. And I hope this has been useful. It's a little bit shorter than the allotted time, but I hope it's been useful. And thanks so much for coming. And feel free to reach out to me if you see me around at the conference. If anybody has questions, also I can. Yeah.
What would you say of the apps that use technologies and safety? Which one do you think is your favorite? And like how they've done it?
So there's like one application that I use a lot is Pocketcast. Is like, and we kind of worked a little bit with their developers on their integration, but it provides this feature where you can sort of share your podcast list. You can sort of synchronize it with people nearby, and we really like this idea of like sharing things, with people around you. So when we were playing with this in the office, like I discovered a whole bunch of podcasts that I never would have found otherwise if we didn't have this technology. So it works perfectly seamlessly.
And so both people would have to have that app.
Yeah, so with the newer messages API and the sort of programmability, I guess you both have to have the app, and you have to be on the nearby page in order to share things. But interestingly, with newer notifications, it sort of changes things, because we're thinking about ways in which you can actually have an asymmetrical model where one person has a podcast with the other one doesn't, and then be able to trigger, telling the other user that they can solve public paths and they can have experiences.
I think that's just more exciting.
Yeah. Yeah, exactly. Because it becomes kind of cumbersome if you're that walk up and user experience doesn't really work if the first step is like, well, let's go to search for copycats and I can install this thing. So really we want to make that kind of one thing.
How much feature area is there with iOS or this application stuff?
Yeah, so the iOS neural messages API is almost complete parity with the core hostile mechanisms of neural messages. The beacon stuff, background support is really challenging in iOS in general, so there is support for backgrounds for that stuff. It's a little more limited than the Android support. But generally, as is really important to us to keep as much parity as we can. So with neural messages particularly, we try to keep that. With the stuff we're going to talk about at I/O, we'll also be announcing that for iOS in the near future as well. Nearby notifications is a real challenge on iOS. We don't really have any way, nearby notifications probably benefits from us using Google Play services more than any other part of what we build. So we can't really find a good way to do that right now on iOS.